Okay, so let's begin. Are there any questions before I start? Okay, so if there are no questions, let me start by recalling what we did yesterday, day before yesterday. So we defined unique factorization domain. So an integral domain is called a unique factorization domain. If every element, we can write it as every non-zero, non-unit, we can write it as product of irreducibles. And it can be done uniquely. So uniquely in the sense that if you can write it as product of irreducible in two different ways, then the length should be same, and after reordering, every element in one side should be an associate of another such expression, another element in such expression. Yeah. And so after this definition, we showed that every PID is a UFD. So in particular, integers and polynomial rings over fields are UFD. So, and then I told you that when R is a UFD, then polynomial ring over R is also a UFD. So this we didn't see a proof, so but this will be done later. But this was just to tell you that there are many examples now of UFD. So polynomial ring over integers, a polynomial ring over in any number of variables over a field is a UFD. Okay, so UFD are more abundant as opposed to PID, which is quite restrictive. Then we also we saw proof that in UFD, irreducibles and primes are same. So primes are always irreducible in any integral domain, and in a PID we saw that irreducibles are same as primes, and we saw in last class that in UFD the same thing holds. So irreducibles and primes are same. And then I told you these two examples of a ring which are not UFD. Okay. So today maybe I'll start by discussing these two examples a little more, and then we will see some more properties of UFD. Yeah, and hopefully a characterizing property of UFD. Another way of characterizing UFD. Okay, so we saw in this example, x times y, we could write it as product of two irreducibles in two different ways, x bar times y bar and z bar times w bar. And here also one can do something similar, but maybe in this example, z square root minus 3, what we can show is that 1 plus square root minus 3 is in fact irreducible, but not prime. Yeah, so let's try to do that. And that will show that this ring is not a UFD. Okay. So this is not. We have already seen that this is not a PID, but now UFD is slightly weaker than PID in some sense, but this is not even a UFD. Yeah. So okay, I was trying to do something more complicated, but maybe we will just do it in a somewhat simpler way. Okay. So suppose you can write 1 plus. So we want to show that 1 plus square root minus 3 is irreducible. So suppose we can write it as a plus b square root minus 3 and c plus d square root minus 3 for a, b, c, d in z. That's how a typical element of this ring looks like. Then we want to show that one of them must be a unit. Yeah. So one can try to multiply it through and compare coefficients is what I was trying to do, but one can also use the norm map. Yeah. So if you look at the norm of the left hand side is 4. Yeah. So apply norm. later. Medhu, sorry, there was someone at the door. So apply norm, and what you get is for the left hand side you get 4, and on the right hand side you will get a square plus 3b square a square plus 3b square, and remember the norm is multiplicative, so you get c square plus 3d square. So what you get is that so the product of these two numbers have to be 4. Yeah. So of course both b and d can't be non-zero, right? Because then both the factors will be at least 3, and that's not possible. Yeah. So we can assume b is 0. Yeah. So we can assume that b is 0. I mean either b or d will be 0. So may assume b is 0. Yeah. So what we get is 1 plus square root minus 3 is a plus c a times c plus d square root minus 3. But now afterwards that tells you that AC has to be 1, yeah, and AD also has to be 1, but AC has to be 1 and AD has to be 1, which implies A has to be plus or minus 1. It has to be a unit, yeah, which implies 1 plus square root minus 3 is irreducible. Yeah, so we have showed that if you write it as product of two different guys, two elements, then one of the factors must be a unit. That's what the definition of irreducible is. Yeah, and then one has to show that it's not a prime element. Okay, so yeah, so so the point is 1 plus. So again, this norm things comes in. So 1 plus square root minus 3 times 1 minus square root minus 3 is 4. Yeah. So that tells you that 1 plus square root minus 3 divides 4. Which is also 2 times 2. Yeah. But 1 plus square root minus 3 does not divide 2. Yeah, because I mean because if you multiply 1 plus square root minus 3 with anything a plus b square root 3 minus any other element, you can't get 2. Yeah, because to get 2, that means a has to be 2, yeah, so you try to solve this equation and you'll get that it cannot be equal to 2 for all A, B, and C. Yeah. So this you can just try to solve yourself. That you can't, for any A, B in integers, you can't get this. Yeah, so this proves, this implies that 1 plus square root minus 3 is not a prime. Does that make sense? So we showed that this is there is an irreducible 1 plus square root minus 3, which is not a prime. But I mean, here you can see that 4 can be written in 2 different ways. Yeah. As product of irreducible. So we already argued that 1 plus square root minus 3 is indeed irreducible. Similarly, you can show that 1 minus square root minus 3 is also irreducible. and their product is 4, you can also show that 2 is irreducible. Yeah, so there are no, you can't write 2 as product of two different two elements in z square root minus 3, which neither of them are unit. Yeah, so even 2 is 2 is irreducible, and so you get two different expressions, and you don't get uniqueness of factorization. Okay, even in, so that was for this example. Even in this other example, sorry, okay, this is not a, yeah. So even in this example, what you can show is x is x bar, rather, x bar is irreducible. Okay. X bar is irreducible in this quotient ring QXY ZW mod XY minus ZW, but not prime. So to show X bar is irreducible, there is a bit of a computation one has to do, but it's not prime is sort of easy. Okay. So what you do is consider the ideal generated by this and go mod it, and what you'll get is something which is not an integral domain. So you will be able to show that z bar and w bar. If you go mod this prime ideal, mod this ideal generated by x bar, then you can show that z bar and w bar are not non-zero divisors. So z bar and w bar are zero divisors. Okay, so you don't get an integral. So that I'll leave it for you to check. Okay. Any questions before I proceed further? Yeah, so I hope everyone is following. So give me some feedback from time to time. Yeah, otherwise I feel like I'm just talking to a.
Is it true for any UFD? Like for any UFD, can we find an element which is irreducible but not prime?
That I don't think that is true. Yeah, so I'll give you a characterization, another characterization in terms of irreducibles and primes. Yeah. So are you asking whether this is so this is obviously necessary, but whether it's sufficient or not? Yeah.
Yes. Yes.
Yeah. So that is not true. You need something more. Okay. So I don't have an example as such in mind, but yeah. So maybe one can try to cook up once I tell you the other characterization. Maybe one can try and cook up. Anything else? Okay. Okay, so before getting to that characterization, I mean, since this is an undergraduate course, I should say a little more about some basics. Okay, so before getting to that characterization, let's look at this proposition about GCD. So you see, the point is in integers, one can compute the GCD in this Euclidean algorithm way, but of course that's not the way we compute GCD. Yeah, we compute by prime factorization. So integers is a UFD, so we can also do this, and this is the more practical way. I mean, if you can compute the prime factorizations easily, then that's a more practical way of. But of course, yeah, factorization need not be always easy. Yeah, so if you look at polynomial rings, then maybe it's not that easy. Anyway, so there are various ways, and so another way of looking at GCD is using the prime factorization. So that is what I'll talk about. Yeah. So let R be a UFD and AB be two elements of R. Okay, non-zero elements maybe non-zero elements of R. So let me just put across here. Then A, you can write it as some unit times P1 power E1 to PR power ER. So see, if A is a non-zero, non-unit, then of course this is definition of R of UFD. You take U to be 1. But if A is a unit, then you take R to be 0 and U to be U to be A. Yeah, so this is just made up to ensure that you can talk about every non-zero element of R. Yeah. Then and B is so R you could just state it for non-zero non-unit. So if A is a unit, you know what the GCD is. GCD is going to be the common divisor. So what is GCD of 1 and 2? It's 1. Yeah. So if one of them is a unit, A and B, then of course GCD is 1. Yeah. 1 is a GCD. But and then you can just say that you assume these A and B are non-zero divisors. Non-zero and non-unit. But anyway, you can combine all that in this statement as well. Okay. And B also you can write it as this V times P1 power F1 to PR power FR, where V are units in R, P1 to PR are irreducible elements of R, and E1 to ER and F1 to FR are non-negative integers. Yeah. So they are allowed to be 0. That's why we can find the same R, the same P1 to PR and same R, yeah? So that we allow some zeros and so on. Okay, and then GCD is basically P1 power minimum of E1 comma F1, P2 power minimum of P2 power F2, and so on, up to PR power ER and FR. You can forget about units. If all these minimums are 0, then this product means 1. Yeah, so empty product is 1. That is what the convention is. So this is, of course, for integers. This is how we compute GCDs, and this is true for UFD. Yeah, and the proof is pretty straightforward. So given any element A, you can of course write it as since R is a UFD, you can of course write it this way. If A is a unit, then you just take U to be A and P1 to N to be 0. Yeah. So the rest of the factors doesn't appear. If A is non-zero non-unit, so if A is not a unit, then of course you take U to be 1 and you get this expression P1 to Pn for En. Okay, and here you can even assume that if N is positive, then E1 to En are all positive integers. And then for B, what you do is B also you can write it as product of irreducibles, but you can also if it is not a unit, if it is a unit, you just write B as V and you put P1. So we will anyway throw in P1 to Pn, and these exponents will be 0 if B is a unit. But if it's not a unit, you can write it as product of irreducibles. Yeah. And if some of these irreducibles are in this list P1 to Pn, then and they will appear with some exponents. You put those down. If none of these exponents, none of the irreducibles are in there, then you put F1 to Fn as 0. Yeah. But there may be more irreducibles other than P1 to Pn. So I just extend that. So let's Pn plus 1 to Pn PR be some other irreducibles which may appear in the factorization of B, and we write it this way. Okay, with whatever exponent. So this I hope is clear. Yeah. So we get. In B, we can write it as V times P1 power F1 to Pn power Fn, Pn plus 1 power Fn plus 1 to PR power Fr, where F1 to Fn can possibly be 0, and Fn plus 1 to Fr are some integers. So they should be positive. Otherwise, you can throw away those PIs. And V is some unit. Okay. So now you just set En plus 1 to Er to be 0, and then you get this expression. So that proves that A and B, you can write it as U times P1 power E1 to PR power ER, and B to be V times P1 power F1 to PR power F1. Okay. Make sense so far? So I'm not doing anything fancy here. Yeah, just trying to write it in a more reasonable. So that both the prime both have the same prime factorization, maybe with exponent 0 if we so require. Now, so we know what the GC. So now we have to show that the GCD is this guy. Yeah. So let dV be this this right hand side here. Right hand side. So d be this this expression. Then of course d divides a1 and a and b. Yeah, because p power minimum of e1 and f1 will I mean the so this is because a is so I don't know so maybe I'll just put so you need some justification here. So a, because a equals d times something. Yeah, what is that something? P1 power whatever this minimum is. So I should have named something. So E1 minus a minimum of E1 comma F1, P1 times this, and so on. PR power ER minus minimum of and you have to put a U as well. ER comma FR. So you have written A as D times some element in R, and hence that tells you that D divides A. And similarly, D divides B. Yeah, so for GCD, we need these two to happen, and if there is any other element D prime which divides both A and B, then I have to show that D prime divides D. Yeah. So let D prime divides A and D prime divides B. Then A we can write it as D prime times A1. So this was the justification for D divides A. Yeah. So now say A is D prime times A1 and B is D prime times B1. By uniqueness of factorization in UFD. So D has this already we are given this prime factorization for D. Yeah. So by factorizing sorry, this is D prime, factorizing D prime. So D prime is a factor of A and a factor of B. Yeah. So D prime has to look like W times. So A and B, the prime factorization is of this form. Yeah. U1 P1 power E1 to U P1 power E1 to PR power ER. Yeah. So D prime. If you look at the prime factorization of D prime, no other primes can appear. Yeah, so D prime in the prime factorization of D prime, we can't get some other prime other than P1 to PR. So it has to be some unit W times P1 power L1 to times PR power LR for some LIs. Yeah, with W unit and LI less equal and also these allies have to be EI because D prime divides A, and Li has to be Fi as well, less equal Fi as well, because D prime divides B. Yeah, make sense? So that tells you that Li is less equals minimum of EI comma Fi, and that precisely means that D prime divides D. Okay. So that that proves that D is indeed the GCD of A and B. Okay, so this is sort of straightforward. It's same proof as in as in integers. If you take two definitions of GCD, one using this prime factor using prime factorization, and the other using this Euclidean algorithm, division algorithm. And if you want to show these two are the same, then or whatever, if you define GCD as this least guy and try to prove that this is GCD, you do the same proof. Okay, any questions so far? Okay, so this was straightforward. So next thing, so remember maybe last class or last to last class, we showed that if a ring admits a Dedekind has a norm, then it is a PID. Yeah, so we stated the theorem that R is a PID if and only if it admits Dedekind has a norm, and we showed one direction, that if the ring has a Dedekind has a norm, then it is a PID. This was to show that this ring Z adjoins 1 plus square root minus 19 over 2 is a PID, but it's not a Euclidean domain. So we showed that the norm, the usual norm, is actually a Dedekind has a norm, but and then we showed that it doesn't have any universal side divisor, so it's not a Euclidean domain. So now we will do the other direction. So we will show that every PID admits a Dedekind has a norm. Yeah, so for this we need to use the fact that PID is a UFD. Okay. So what is so this is the definition of the norm. And we will show that this norm is a Dedekind has a norm. So remember, what is a Dedekind has a norm? So it's in a Dedekind has a norm, everything is a map to positive integers. Yeah, so nothing, no element of the ring has norm 0. Yeah. So every so norm anyway, the definition we have taken is it's a function from non-zero elements of the ring R. So it's slightly different. It doesn't matter. I mean, in this textbook, Dummett and Foote, they declare norm of 0 to be 0. Yeah, but we don't even define the norm of 0. Yeah, so it doesn't matter. So what we do is for units, we declare its norm to be 1. And for any element, any non-unit, so x, using the black pen. So x, x non-unit, then we can write x as product of irreducibles, p1 times pn with possible multiplicity, but we don't really care about it. So maybe if it has m irreducible factors in its factorization, then we send it the norm of x is 2 power n. Yeah, that's what. So of course, this uniqueness of factorization into irreducible factors tells you that this is well defined. Yeah, you can't have two factorization with different lengths. Yeah. So it's a well defined function. Next thing we have to show is it is Dedekind has a norm. So Dedekind has a norm means if we take so let x, y be in R, then what it says is that either x divides y, or there is some linear combination of x and y has norm smaller than norm of y. Yeah. So maybe it was in terms of AB. So let's just do that way. So AB is in R. So either B divides A, or there exist xy in R such that want to show. So we want to show this. Yeah, want to show such that ax plus by, norm of this, which is our R here, is less than strictly less than norm of B. Okay. Yeah, so hopefully this should be okay. So so suppose B does not divide A. Yeah. Um, so suppose B does not divide A, then we want to show that uh, uh, want to so then we want to show that exists R in the ideal generated by AB such that the norm of R is less than norm of B. Yeah. So yeah. So how do I? Yeah. So one has to look at irreducible factors and so on. Yeah. Yeah. So basically, you look at yeah. So 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 let D be the GCD. So the ideal generated by AB is same as D. Yeah. So D is the GCD of AB. We are in a PID, so we have this. So uh, of course D divides B. Yeah, because D is the GCD, D divides B, and B does not divide D. Why? Since uh, if B divides D, that since if B divides D, this will imply that uh, uh, B is also the GCD of then B and D are associates. Yeah. So this will imply since if then
Imply B divides A.
yeah, which will imply B divides A. Yeah, so then this will imply that B divides A directly. Yeah, so which will be a contradiction to our assumption. Yeah, so we have D divides A, but but uh, but B does not divide A. Yeah, so if we look at prime factorization of D, so let D equals P1 to Pn, and and then of course then B equals P1 to Pn times something, yeah, times Q1 to Qm, because D divides B, so the and M has to be at least 1, yeah, because if there is no Q1 to Qm appearing, then that tells you that uh, B will divide D, yeah, which implies norm of D, which is 2 power n, is strictly less than norm of B, which is 2 power n plus m. Okay, so that shows that and D of course is ax plus by for some xy naught, because D is in the ideal generated by AB. Okay, so that completes the proof. Is that okay? So so if once you have once you have this factorization, then this is straightforward. So this is how. So we have constructed one Dedekind-Hasse norm on a PID. Yeah, so now that theorem which we stated, that R is a PID if and only if it admits Dedekind-Hasse norm, is now complete.
So simply assigning n would have worked.
Say that again.
Like, why do we need 2 power something? Like, we could just assign n. Like, n is also less than n plus n.
Yeah.
Number of irreducible matters.
Yeah, so maybe 2 power n is a overkill. Yeah, maybe n plus 1, just so that units will have different norm. I don't know if it will interfere. Yeah, so even n plus 1 will work, because yeah, that's all we care. Yeah, so you can take n plus 1 or something like that. Yeah. I'll have to be careful about units given same norm as one of irreducible. Yeah, that's why I'm just trying to make it bigger than 1. Yeah, so you're right. One can take n to be nx to be n plus 1 as well. This should work.
But nx 2 power n will make it a kind of like multiplicative
Yeah,
when we are co-prime and all.
Yeah, so this norm is multiplicative, but Dedekind norm, the way it was defined, was not really needed to be multiplicative, I think. So here you can say it admits a multiplicative Dedekind-Hasse norm. So maybe, I think, yeah, so I don't think multiplicative is necessary for this property. But maybe Dedekind-Hasse norm, the way it was defined by Dedekind and Hasse, was multiplicative. Okay. Yeah, so the only advantage of doing this is that it makes it multiplicative. But for this purpose, it's not essential. The only thing we care about is this division algorithm kind of thing works. Any other question? Okay, so yeah, so this is the characterization I was talking about. Okay, so what is the time? Maybe I will do it after the break or before the break. So maybe one direction we can do it before the break, and then we'll take a break. Okay, for the other direction. Okay, so let R be an integral domain. Then R is a UFD if and only if these two conditions holds. So every irreducible element in R is prime, and you need this other condition. Every strictly increasing chain of prime ideas is of finite length. Yeah. So you can't get an infinite sequence of infinite chain of strictly increasing prime ideas. Okay, so let's see the forward direction, and then we will do the backward direction after the break. So forward direction, number one is, so yeah, we assume R is UFD and we want to show 1 and 2 holds. So 1, of course, we have already proved. For UFD, we have already shown that every irreducible element is in R is prime. And so we have to show that every strictly increasing chain of principal ideas is of finite length. Yeah. And then we will prove the converse. So let this be a strictly increasing chain of prime ideas. Then we will show that it can't go forever. Yeah, and this is with the fact this will I mean, one can actually give a bound on how long this length can be. Yeah, so it depends upon basically prime factorization of x1. Yeah, so so since R is a UFD, let x1 be product of these. So you write x1 as product of irreducibles, p1 to pn. Pi is in R irreducibles. Okay, so now x1 belongs to x2, implies that x2 has to divide x1. Yeah, so this implies x2 divides x1, and it's a x1 is a proper ideal of the ideal generated by x1 is proper ideal of x2. So they um, also and and the ideal generated by x2 is not equal to ideal generated by x1. So it's a proper ideal implies that x2 does not divide, so x1 does not divide x2. Yeah, so x1 does not divide x2. Yeah. So that tells you that the number of the prime factorization of if you look at so maybe the first statement tells you that these two together will tell you that x1 is x2 times some y, or maybe I'll just say y1. I don't know if I want to proceed for too long, but let's just say for y1 in R, for some y1 in R, where y1 is not a unit, is non-zero, non-unit. I mean, we can, if we assume x1 is non-zero, yeah, so we can always assume, okay, so let's just throw in this, yeah. So we can always look at the second term of the sequence if you are doubting that x1 may be 0. Yeah. So y1 is non-zero, non-unit. So now if you look at the so this tells us that number of irreducible factors in x2 is strictly less than n. Yeah, by uniqueness of prime factorization. So you look at prime factorization of x2 and prime factorization of y1. So should I do it in more detail? Okay, maybe I'll since first time maybe it's like a GCD kind of argument. So you just write let x2 be equal to q1 to qr, and y be equal to maybe qm, and y be equal to r1 to rk, okay, as product of irreducible, then you get that p1 to pn is equal to q1 to qm times r1 to rk. So this tells you that m has to be less than, and uniqueness of factorization tells you that m has to be implies m plus k equals n, which implies m is less than n. Yeah, because both m and k are greater or equal 1. Y is irreducible. Yeah, so x2 has less number of irreducible factor. So and similarly, x3 number of irreducible factors of x3 is less than number of irreducible factors of x3 is less maybe I'll just use this notation, is less than number of irreducible factors of x2 and so on and so on. Yeah. So that implies that eventually, I mean, the number of factors, so the length of the chain can at most be n plus 1. Yeah. So the length GTH length of the chain or chain of the prime ideals, the principal ideals. Okay, principal also starts with P. Principal ideals. X1 contained in X2 can be at most n plus 1. Yeah, so maybe you keep on decreasing at most n actually. Eventually, if you run out of all the irreducible factor, it will become a unit. Yeah, can't be even n plus 1. Okay. So that proves number 2. Yeah. So maybe after the break, we'll complete the proof of the other direction. Okay, so let's take a break for take a break till 12:05 or 6. Yeah, so I'll come back at 12:05 or 6. Okay, so do you have any questions before we resume? So okay, let me just check the chat. Yeah, so there is nothing in the chat box. So I suppose there are no questions. Okay, so let's do the other direction. So we saw the forward direction. Now we will assume that the ring has these two the integral domain has these two properties, that every irreducible element is prime, and every increasing chain of principal ideal is of finite length. Strictly increasing chain of principal ideal is of finite length. Then we want to conclude that R is a UFD. Yeah. So okay. Just draw some line. Separate it. Okay. So for backward direction, this is maybe too right. So we want to show that we can construct a factorization, and then we will use. So second property will be used to show there is a factorization, and then the first property will be used to show that the factorization is unique. Okay, so let X be some element of R, non-zero, non-unit. If we so want to show X, X has want to show X is a product of irreducibles. So first this, and then uniqueness. Yeah. So if X is irreducible, then done. Yeah. So then there is nothing to do. You write X equals X. Otherwise, there exists let's say maybe, yeah, x1, y1 in R, such that x equals x1 times y1, where x1 and y1 are non-units. Are non-units, right? So since it's not irreducible, that means you can write it as product of two non-units. That is the definition of reducible, if you like. Yeah, so this implies that the ideal generated by x1, or maybe I'll write it this way. So ideal generated by x is contained in x1 because x is a multiple of x1. But since y1 is a non-unit, we have this inequality. Yeah, I mean the ideal generated by x1 is not equal to the ideal generated by x because x1 you can't write it as x times something because why, since y1 is not a unit, non-unit. Yeah, so we are going to construct a chain of principal ideas. Yeah. Now, if x1 is, so for what I'll do first is, so that x we can write it as irreducible times something. Yeah, and then that something again we will write it as irreducible times something, and so on. That is how we'll produce. So so if x1 is irreducible, then and then x and then okay, so maybe then we have shown that x equals p1 times y1, where p1 is irreducible and y1 belongs to R. p1 is irreducible in R and y1 is some arbitrary element in R. Otherwise, so our immediate goal is not to show that x is a product of irreducible, but trying to find a irreducible factor of x. So there exists irreducible such that x is irreducible times something. Yeah? Otherwise, what we do is continue this this step. So x1 we can write it as x2 times shown that this happens with p1 equals x1. Yeah. Otherwise, x1 we can write it as x2 times y2, where x2 y2 are non-units. So if x1 is not irreducible, then we can of course do this, and this implies that x1 is contained in x2 and it's proper. So this is a strict inequality by the same logic. Yeah, x1 is a multiple of x2 and the other factor is a non-unit. Continuing this way, so again, if x2 if x2 is irreducible, then we can stop. But if not, we keep continuing this way. This way. Sorry, this way. We obtain a chain strictly increasing strictly increasing sequence of principal ideals. So the first term was x and properly contained in x1, properly contained in x2, ideal generated by x2, and so on. So by 2 it must stop. So by 2 it must stop, say at xn, say at nth spot, nth spot, let's say. Then it stops means you can't. So what it means is that xn must be irreducible. So it stops means it has to, eventually this we won't be able to find. So the only way it can stop is when xn becomes irreducible. Yeah, then we can't factor it as product of something. Xn plus 1 which is irreducible, and yn plus 1 which is also xn plus 1 which is non-unit, and yn plus 1 which is non-unit. Okay, so whenever xn is not irreducible, we can keep on going. So then what it means, so that tells you that x, which is x1 times y1, which is, and then x1 is x2 times y2 times y1, so on, is xn times yn minus 1 y1. Yeah, so so x is this, which implies x is p1 times some y, where p1 is irreducible and in R, and y is some element of R. Yeah. So maybe I should have put this as some claim somewhere. Yeah. So maybe yeah. So claim is so I'll just put it here in somewhere in the middle. Claim x equals p1 times y, where p1 is irreducible and y is some element of R. Okay. So far what we have done is prove this claim. Yeah. So we have this. So this claim is done with p1 equals xn and y equals product of y1 to yn, y1 to yn. Yeah. Okay. So maybe I'll move to the next board. So far we have used only property 2. Yeah. So again we will use property 2 to make it as product of irreducible. So final claim is we can write it as product of or whatever the other claim, not the final claim, but uniqueness is also there. X equals p1 to pn, where pi's in R are irreducible. So what is the proof of this claim? So of course, by our previous claim, x equals p1 times y1 for some p1 in R irreducible and y1 in some elements in R. Yeah. If y1 is a unit or even irreducible, then we are done. Yeah, then done. Otherwise, sorry, I should have continued with black, but let's not. Yeah, so let's just continue with red now. Otherwise, we can write y1. Y1 is a non-zero non-unit. Yeah, and not irreducible. So if y1 is irreducible, then also we are done. So y1 is non-irreducible. So that implies then that y1 we can write it as p2 by the claim here times y2, where so even if it is irreducible, we can write it this way: p2 irreducible and y2 in R. Yeah, and what we get is and continue this way, until this way if y2 and so on are if y2 is not irreducible. Yeah, so let's just do it till we get irreducible. So of course, this process gives us, so the point is this has to stop by the same reason. Yeah, so note that this chain of ideals, so x, maybe we can start with x. Yeah. So x, the ideal generated by x is contained in the ideal generated by y1. Yeah, because I mean, x is a multiple of y1 and it's not equal, because if it were equal, then that would say that because p1 is irreducible. Yeah, it's not a unit. p1 is not a unit. And similarly, y1 is contained in y2, because again y2 is some because y1 is a multiple of y2 and p2 is irreducible. So and so on. So strictness is true because p1, p2 are irreducibles and hence not units, and hence not a unit. Okay, so again by 2, this has to stop. At say nth stop, at say after n steps, then we get x, we can write it as P1 to Pn. Okay, as product of product times okay, maybe Yn as product of irreducibles. Irreducible. Okay. Any questions so far? Yeah, unfortunately, I kept it a little too large to make it small. Further is a bit complicated, but anyway, with these things we have shown that everything is product of irreducible. Now the point is irreducibles primes will tell us that this factorization is unique. So that proof is similar to the PID case. Yeah. So let me. So what I'll do is I'll leave that as an exercise. Yeah. So yeah. So maybe homework. So maybe yeah. So I'll leave it as an exercise and take a feedback and check if you can do it. So I'll not put it as a homework. Show uniqueness of prime of irreducible factorization using one. So point is, if you have two factorization P1 to Pn and Q1 to Qm, then note that Pi's are not just irreducible, they are primes as well, because we are assuming all irreducibles are prime. So P1 will divide the product of Q1 to Qm, and then it has to divide one of these Qis. So the way we did it for PID, yeah, in C PID and PIDs UFT's proof. Okay, so it's exactly the same proof. Yeah, this is the only thing we are using. Okay, any questions? Yeah, so this is the time to ask questions. So I'm not going to do anything further today. So if you have questions, just let me know. And if you don't have questions, then we'll stop here. So next time, maybe we can think about constructing a ring, which will have this. We can ponder about this property as well. Constructing a ring which in which every irreducible is prime, but maybe it's not UFT. So maybe the second property fails. Okay, so I guess there are no questions. So let's stop. See you on Friday. So see you tomorrow.